Alright, so this video cast is a overview of stoichiometry, a review of general stoichiometry, and then using limiting reactants. There are 4 steps in the stoichiometry process. First of all, write the balanced chemical equation. Many times that's given to you. Second of all, convert to moles, usually using the periodic table because many times they give you grams, and so you have to go from grams to moles. Third step, using the mole-to-mole ratio from the balanced chemical equation, therefore using the coefficients that are in front of the reactants or the products. And then fourthly, convert to the asked for units, which many times is grams at this stage in your chemistry career, but it could also ask for molecules, ions, particles, and eventually it'll ask for like liters or other types of volumes of substances as well. So those are the 4 steps, and we're going to keep those aside as we work this practice exercise number 1 right here that happens to be on page 106 if you're in the 13th edition of the book. So practice exercise 1 says, propane, C3H8, is a common fuel used for cooking and home heating. What is the mass of O2 that is consumed in the combustion of 1 gram of propane? So following the steps, the first thing we want to do is write the balanced chemical equation for the combustion of propane. Propane is C3H8, and in a combustion reaction we always react it with oxygen, and the products of hydrocarbon combustion are always carbon dioxide and water. So we put those 2 on the right hand side. Best way to balance these always is alphabetically, so carbon's first, so put a 3 right here. Hydrogen second, put a 4 right here, so we've got 8. Add up the oxygens on this side, 6 plus 4 is 10, so we need a 5 right here. Step number 1 is done, the balanced chemical equation. Step number 2, convert to moles, and in this case we're given 1 gram of propane. So way over here on the left-hand side I put 1 gram of the C3H8. Put a multiply sign, put a line right here, and then if you're not sure how to, or if you forgot how to convert to moles, remember you can always go from here, from grams to moles by putting 1 mole on the top and the molar mass on the bottom. And remember the molar mass comes from the periodic table. So we'll put 1 mole of C3H8 here on the top, and on the bottom we'll put grams of C3H8. And if you add up 3 carbons and a hydrogen, remember each carbon is worth 12, each hydrogen is worth 1, multiply this one by 3, this one by 8, and add them together, you get 44. So there are 44 grams in 1 mole. Step number 2 is done. We've converted to moles in this step. Step number 3 now is the mole-to-mole ratio from the balanced chemical equation. So put a multiply sign, put a line. Take the units that you have and place them in a position where they're going to cancel. Take the units that you have and place them in a position where they're going to cancel. And right now the units I have are moles of C3H8. So I put those on the bottom of this fraction because I want them to cancel. And then put your desired unit here on the top. My desired unit, I go back and reread the question, and it wants to know what O2 is consumed. So I'll put moles of O2 up here on the top because that's my desired piece that I want to know. Numerically, I want to find these in the balanced chemical equation. There's a 1 in front of the C3H8. In front of the O2, there's a 5. So I'll put a 5 right here. And I'm now done with step number 3 where I did my mole-to-mole fraction or my mole-to-mole ratio. Last step, convert to the asked for units. And if I go back and reread the question, it says what mass of O2 is consumed. So mass is what I want to know. Right now, if I stop that, I have moles of O2, so I've got to go from moles to grams. Moving from moles to grams, remember I have to use my periodic table. Look inside here. Going from moles to grams means mole on the bottom, molar mass on the top. So I'll put 1 mole of O2 here on the bottom. Grams of O2 is my new set of units. I've got to add up O2 on the periodic table. Oxygen is 16 times 2 is 32. Now on your calculator, 1 times 1 divided by 44 times 5 divided by 1 times 32 divided by 1. I believe you end up with about 3.64 grams of oxygen once you run it all the way through your calculator. That's a review of the 4 steps for stoichiometry, and now we're going to take it to a new level by talking about times or possibilities when we might have more than 1 amount of a reactant.
And that, where it says like the 5 moles of O2, how does that just like disappear, I guess?
So this number right here came from the coefficient. The question is, where did this 5 and this 1 come from, I think? And so they came from the ratio of needing 5 of these for every 1 of these. And notice in the units, the grams cancel with the grams here. The moles of these cancel with the moles of these. And these moles would cancel with these moles right here. So your units would go away. This proportion, or this ratio right here, comes from knowing that there's this thing called the law of conservation of matter that says you can't create or destroy any matter. Whatever's on this side can simply be rearranged to be on this side. So it's not like I'm getting rid of something. I'm just taking these 5 O2s right here and just dispersing them over here, and they become something else. So that's where those numbers come from. Good question. All right, so the next one is stoichiometry problems now, where I'm given more than one amount of a particular reactant. Stoichiometry problems given more than one amount. These are also known as limiting reactant stoichiometry problems, and they follow the same sequence of events where you have a balanced chemical equation first, or you have to balance the equation if you don't. Second of all, you have to convert to moles, but now you have a step 2.5. And in step 2.5, you have to find which reactant is going to limit the production of whatever you're asking about. So finding the limiter, many people find this one of the more difficult things to do in this chapter. Step number 3 is the same, a mole-to-mole ratio from the balanced chemical equation. So you can see it's the same right here, step 3 and step 3. And then step 4 is to convert to the asked for units, which many times is grams. Sometimes they'll just say how many moles is it, and then you're done. You don't even have to do step 4. So as like a practical example of what this really means, let's pretend that we're a factory that makes cars, toy cars like this that have, like a really neat little shape like this. And you'll notice that the car is composed of a car body that looks like this, and it has 4 wheels on it, 1, 2, 3, 4. Okay? And let's say that you worked at the car body factory and the car manufacturing factory, and your supervisor ordered you 10 car bodies, and then thinking that it would be, like a smart thing to do, they also ordered 10 wheels. 10 car bodies, 10 wheels. Well, make me 10 cars, please. Can you do that? Doesn't work out that way, right? Because how many wheels do you need per every car? You need 4. And so what's the minimum, or let's say maximum, number of cars that I could actually make if I only had 10 wheels? I could make 2, maybe even 2.5 cars, I guess, right? Because I could make a half a car with only 2 wheels on it, although it really wouldn't be a car because it wouldn't work very well. You just did limiting reactant stoichiometry, because this one right here is called our limiter, because it limits the production of how many cars I can make. Now, one of the trickier questions is, how much excess car bodies do I have left? Can you figure that out too? Well, I used 2 car bodies up, actually 2.5 car bodies, right, if I could make a half a car. So really, I'd probably have, 7.5 car bodies left. Well, this is the type of thing that we're going to do, except for this time, we're going to do it with chemicals and things that are micro or nanoscopic. Here's our balanced chemical equation. We're going to use N2 plus 3H2 makes 2NH3, and we're going to ask the question, how much of this stuff can be made? Just like we asked how many cars can be made. But this time we're given that we have 10 grams of hydrogen, and we're also given that we have 28 grams of nitrogen. 10 grams of hydrogen and 28 grams of nitrogen. Let's follow through the steps to answer these questions. First of all, which one is the limiting reagent, or which one is the limiter, like these 2 things? Which one limited the reaction? Step number 2, what's the number of moles of NH3 that can be produced? What's the maximum yield over here that I could make? And then lastly, what's the leftover of the excess reagent? How much is left over of the thing where there is too much? So I'm going to move this over to this side, and then I'm going to work the steps that I just outlined over here one at a time, and I'll highlight them from right here as we go along. So step number 1, write the balanced chemical equation. That's done for us, so I'll just highlight that balanced equation, done. Step number 2 then, when in doubt, convert to moles. And we have 2 things to convert to moles. So way over here on the left-hand side of your paper, start with 10 grams of H2, put a multiply sign, a line, skip a line, 28 grams of N2, put a multiply sign, put a line. And now we want to take and convert to moles. And so I'll look up each one of the steps in here. And when I go from grams to moles, remember mole goes on the top, and then molar mass, which is from the periodic table, goes on the bottom. So for each one, I'll put moles of the substance here on top, moles of the nitrogen here on top, and I'll put grams of hydrogen here and grams of nitrogen right here. 1 mole, 1 mole. Looking on the periodic table, hydrogen has an atomic mass of 1, and it's H2, so 1 times 2 is 2. And then nitrogen, if I look at that on the periodic table, is 14, and there's 2 of them, and 14 times 2 is 28. So converting to moles now, I have 10 divided by 2, which is 5 moles of H2. 28 divided by 28 is 1 mole of N2. All right, so I have my moles in step number 2 now. I converted to my moles, and I'm on to step 2.5, how to find the limiter. Well, here's the quick, easy, dirty way to find the limiter. Take your number of moles and divide it by its coefficient. Divide it by the coefficient from the balanced chemical equation. And so if you look at the balanced chemical equation, 3 is for hydrogen, 1 is for nitrogen, and then after you do the division, then you have to decide which one is smaller. 5 divided by 3 is actually like 1.666, something repeating. 1 divided by 1, of course, is 1, and then you have to decide from that which one is smallest. 1.6 or 1? Well, this obviously is smaller, and so the smaller one limits. And I've answered question A right now. My limiter is the smaller one after I divided by the coefficient.
How did you get the 3 and 1? I missed that part.
So I found the 3 right here from the coefficient, or the number in front of H in the balanced chemical equation. I found the 1 from the number in front of the reactant nitrogen in the balanced chemical equation. That was a good question. Okay, I'm done with step 2.5, and I answered letter A as to what my limiter is. Now I can go on to, let's see, I'll just put the answer to A right here. The answer to A, my limiter is nitrogen. Now let's answer letter B, which says how many moles of NH3 are produced. And if I'm looking at my steps, I'm at step 3 right here because I found my limiter. What is the mole to mole ratio? So once you've found the limiter, work the rest of the problem based on that number of moles that it had before you divided it by the coefficient. Work it based on the number of moles you had before you divided by the coefficient. And so way on the left-hand side right here, write down 1 mole of N2, put a multiply sign, put a line, put moles of N2 in a position where it's going to cancel, and put moles of your desired unit here on top. What do I desire to know? Go back and reread the question. I want to know moles of NH3. So the thing that I want to know is NH3, so I put that on the top, NH3. Now I get the numerical units right here from the balanced chemical equation, because this is step 3 now, mole to mole ratio. That's what that always means. Look at these numbers. And so for NH3, there's a 2 in front of it. For N2, there's a 1 in front of it. And so to answer the question, how many moles of NH3 would be produced, it would be 1 times 2 divided by 1, which is 2 moles. And so to answer letter B, how many moles of NH3 are produced, all I did was step 3. They didn't ask me to do a step 4 this time and convert it to some other units, but they might. They might ask how many grams is it or how many molecules is it, but that's what they asked this time. Letter C is the trickiest one. This one says, how much leftover excess reagent is there? And I know my hydrogen's my excess because when I divided it by the coefficient, it ended up being larger. But how do I figure out how much is in excess? Here's the steps. First, take your limiter. Write that number down way here on the left-hand side. 1 moles of N2. Put a multiply sign, put a line. This time we will compare the limiter to the excess reagent in the formula or in the balanced equation, and we will determine how much of this will actually react. And so take the units that you have and put them in a position where it's going to cancel. Units that I have, put them in a position where they're going to cancel. And then on the top, put the units of the excess reagent, H2, right here. For every 3 H2s, there is 1 N2. 1 times 3 divided by 1 is 3. So that means I will use 3 moles of H2. This is how much I'll actually use. Now I'm going to highlight this one, because this is how much I actually will use. This is how much I started with. Start, use. How much is left? How did I figure that out? I took the amount that I started with, 5, and I subtracted it from it the amount that I used. And 5 minus 3 means 2, and so there are 2 moles that are excess or 2 moles that are left over. Go back here and just notice the steps that I did. Notice I always started with the limiter. And then when I wanted to know the excess, I compared it to the excess reagent. All right, we're going to go on and we're going to do a scary problem now from the textbook, one of your homework problems, which happens to be number 77 from the back of chapter 3. And I'm going to follow through and do all of these steps once again right here, 1, 2, 2.5, 3, and 4. And they use big scary numbers. Actually, it happens to be little scary numbers that are like decimals and are confusing because your calculator wants to put them in scientific notation. But we'll try to limit that. Number 79, and I actually have the question here to put on the video cast for you as well. It's right here, and if you look at it in your book, I believe it's on page number 118 if you're in the 13th edition. This one says, the fizz produced when an Alka-Seltzer tablet is dissolved in water is due to the reaction between sodium bicarbonate, NaHCO3, NaHCO, and citric acid, HC bunch, H bunch, O a bunch. Okay, and then here's the balanced chemical equation. Ooh, good, I'm not going to have to do step number 1, right, because it's already balanced for me. In a certain experiment, 1 gram of sodium bicarbonate and 1 gram of citric acid are allowed to react. So 1 gram and 1 gram. Step A, what is the limiter? That's just what we needed to find out last time. Letter B, how many grams of carbon dioxide form? It wants to know how much of this forms, and it wants to know grams. Okay. And then letter C, how many grams of the excess reactant remain after the limiter is completely consumed? So 3 questions, just like we did for our example problem a little bit ago. And we're going to start with number 1 right here. Step number 1, I'm going to rewrite the reaction 3 NaHCO NaHCO3. And then we've got H3C6H5O7 arrow. And then we've got 3 CO2s. And then we've got 3 waters. And then lastly, we've got a Na3C, I believe that's a 6H5O7 over here. So there's step 1 done, balanced chemical equation. Step number 2, start way on the left-hand side, outside, and leave lots of room. I'm going to ignore sig figs right now. I'm going to put down 1 gram of NaHCO, put a multiply sign, put a line, skip a line, 1 gram of the H3C6H5O7, multiply sign, put a line. Since we're going from grams to moles, you'll have to look on your periodic table. And on your periodic table, you're going to have to look up how to convert from grams to moles again. So from grams to moles, 1 mole goes on the top, the molar mass goes on the bottom. So we'll put 1 mole of this NaHCO3 on the top, 1 mole of the H3C6H5O7 on the bottom, grams down here, grams down here. I got to add up 1 Na, an H, a C, and 3 O's on the periodic table. That's a lot to add up on here, so I'm going to do that for you. Turns out to be 84 grams to do that. And then this one's even worse. 3 H's, 6 C's, 5 H's, and 7 more O's. Got to add all those up on the periodic table, and that one adds up to 192. Watch those, because those are a frequent source of error for people on quizzes and tests, adding these things up. Just be really picky with your calculator on that. Okay, so 1 divided by 84 in decimals, this turns out to be 0.0119er. And for this one, 1 divided by 192 in decimals ends up being 0.005208. Lots of decimals and small numbers, and now it's not quite as easy to see which one's going to be the limiter because they're not nice whole numbers. So we're done with step 2. We converted to moles, and it was painful. Now we're on to step 2.5, find the limiter. Looking back at your notes, what are your steps to determine what the limiting reagent is? Divide the moles by the coefficient, right? And the smallest is the limiter. Okay, so now we need to take this number and divide it by the coefficient in the balanced equation, which is 3. Okay, and we need to take this one and divide it by its coefficient, which is 1. So this one's going to end up being obviously 0.005208. This one you're going to have to do on your calculator, and it's a lot of numbers to push in, so I'll do it for you. This divided by 3 ends up being 0.00396. And this number and this number need to be compared, because you need to decide who is the smallest. Well, 0.00396 is the smallest, and so therefore the answer to letter A, or the first part of the problem, is that the NaHCO3 is my limiter, because that one's going to end up being the smallest after it's divided by its coefficient from the balanced chemical equation. Now I will work B and C based on this guy right here, because I know that's the one that's going to be used up or run out, just like our tires in the example where we're making cars. All right, let's take this number and rewrite it over here. Start way on the left-hand side, 0.01190, and this is moles of NaHCO. And then going back to reread the question, it says, how many grams of carbon dioxide can form? And so in step 3, I'm going to do a mole-to-mole ratio between this guy and the carbon dioxide. This is my desired unit up here. So take the NaHCO3 moles and put that down here in a position where it's going to cancel. Put your desired units up here, and both of these are moles. And since it's step 3 mole-to-mole ratio, I always look in the equation to find those numbers. What number's in front of CO3? I'm sorry, CO2. What number is in front of NaHCO? Oh, it's a 3-to-3 ratio. Very nice. And now if the question just said how many moles of carbon dioxide are going to be produced, you'd be done. They were evil, though. They did not say just moles. They said a unit called grams. So you need to do one more step, and you need to go from, notice your moles here cancel with here, from your moles of CO2 to grams of CO2. Now, if you forgot how to do this, because it's kind of confusing because there's a lot of steps, remember all you're really doing in this portion right here is using the mole wheel to go from moles to grams right here. So molar mass goes on the top, 1 mole goes on the bottom. Add up CO2 on the periodic table, and 1 mole for 1 carbon and 2 oxygens, it adds up to 44 grams. So 0.0119 times 3 divided by 3 times 44, I'll do the math for you. It ends up being 0.5236 to 4 sig figs grams of CO2. We're almost done. Last, most difficult problem. This is usually the part C right here. This separates the A's from like the B pluses. So trickiest part, how much is left over? Remember when we did the leftover question last time, you always start with your limiter. Start with the amount of limiter that you have. So start over here with the 0.01190 of the NaHCO. And notice I always start with moles again, right? Always start with moles, moles, moles of the limiter. Multiply sign, put a line. Put the units that you have in a position where it's going to cancel. Moles of Nahako right down here. And then your desired unit up here is the excess reagent, whichever one there's too much of, because we want to know how much of that excess is going to be used. And my excess reagent is this thing, this big, long, scary equation, which is H3C6H5O7, called citric acid. And then I look on the balanced equation to find the numbers for these. Nahako here has a 3 in front of it. Citric acid has a 1 in front of it. 0.01190 times 1 divided by 3. A lot of numbers to put in your calculator. I'll do this for you. It turns out to be 0.00396. And this is the moles that are used up in the reaction. Kind of like when we were making cars, with cars and tires. This would be like how many car bodies were used up. So, if I used up this many, and if I started originally with this amount right here, here's how much I originally had, here's how much I'm going to use up. How would I find out how much I have left from those two? Take this one, divide it by the amount that I used, like my 9, sorry about my 9 right there, 0.00396, and subtract or find the difference between those two. And my leftover is 0.001248. Now, most questions end right there, and they just say how many moles are left over. This one's particularly mean because they want to know how many grams are left over. And so you need to convert this from moles to grams of this H3C6H5O7. There's 192 grams in a mole there, and it turns out that's how many grams you have remaining at the end of the reaction. Thanks for tuning in and learning a lot about limiting reactant stoichiometry problems.